Good evening, Level 2s. So we're going to look at nuclear energy now as our last topic in atomic physics this year. And first up is the mass energy in a nuclear reaction. So it was rather puzzling for physicists to work out what was going on. Why was energy being given out when radium and things like uranium were decaying? And the answer lies in Einstein's theory of relativity, that mass is a form of energy, or energy and mass are conserved in a reaction. So we'll look a bit further at this. Total mass of a stable nucleus is always less than the sum of the masses of the parts that make it up, which are the protons and the neutrons. So if you look at this diagram on the left, this might be a lithium, let's say a lithium nucleus, for example. It's got 3 protons, 4 neutrons. And in order to break it apart, because it is a stable nucleus, it is not an isotope that is a radionuclide, it's not radioactive. So we'd need to add binding energy to it, which is basically just energy, in order to break it up into its 3 protons separately and 4 neutrons. So these things together here, if you added them, the mass of that plus the mass of that plus the mass of that and so on, as separate entities, this would have a greater mass than if you put all of this together. This would have a smaller mass in the nucleus. So what that meant was that energy would need to be added to the left side of this equation in order to separate the protons and neutrons. And conversely, if this was what we started off with on the right, we would, and the protons and neutrons went to form a stable nucleus, then energy would be given off. So that's what we're talking about here. So in a nuclear reaction, the rest mass of the products can be greater or smaller than the reactants. And the difference in that loss or gain of energy is given by E equals delta mc squared. So E here is the energy given by the loss or the gain. Delta m is the difference in the mass. And c is the speed of light, 3 times 10 to the 8 meters per second squared. Don't forget to square. So let's look at this example. So Rutherford, we already have seen this earlier on in this topic. Rutherford found that alpha particles in a jar of nitrogen gas actually produced oxygen and hydrogen. So you might want to pause here and try and write that equation for yourself, because we have done it before, and now's a good time to check that you can do it. So check your equation. So you're starting off with alpha particles inside a nitrogen gas here, and that would produce the hydrogen particles and the oxygen. Did you note that there was a number 17 here? And that is because the 4 plus 14 has to balance. It's total 18 at the top, 17 and 1 has to be 18. So we know it's an isotope of oxygen. We have covered this reaction before. Now, if we look at the rest masses of each of these individual parts on the left and again on the right, we'll find that the total rest mass before the reaction, so in other words, we take the rest mass of a helium particle, an alpha particle, a helium nucleus, and it's that value, and we add to it the rest mass of a nitrogen particle, and we end up with a sum total of 29.89535 times 10 to the negative 27 kilograms. So really small. But then if we look at the total rest mass after the reaction for oxygen, or this isotope of oxygen, and a proton or hydrogen particle, then we end up with a total of this number, 29.89 799. So you can see that is slightly bigger than the one on the right. So in other words, mass of the products was actually more. And we can find the difference between these two numbers. We subtract them and we get this number here, 0.00264 times 10 to the negative 27 kilograms. So that means we could actually calculate then how much energy this increase in mass is equivalent to. Using the equation above, E is equal to delta mc squared. We substitute in the difference of the masses, multiply by c, and we square it. Don't forget to square. And we get this value, 2.38 times 10 to the minus 13 joules. So that's the amount of energy that is equivalent to this amount of, to that mass, or increase in mass. Now, another thing we just need to understand here is that the stability of a nucleus is directly related to its binding energy per nucleon. Now, we're not going to look at this concept per se this year. We'll look at it in greater detail in level 3. But it's worth noting that on the periodic table, if you have really heavy elements, or really heavy isotopes of elements, that they have a lower binding energy, and that iron has the highest binding energy of all. And then if you work from hydrogen up towards iron on the periodic table, that these elements have got a lower binding energy. So what this really means is that iron has got the prime position, as it were. The most stable isotope that exists is iron 56. And so what's going to happen is that any isotope that is smaller than iron will typically bind with another isotope and produce something larger to become, or to get closer to, as it were, this iron over here. And everything on the right, which is unstable, all these isotopes on this side, will break down. Okay, and this process is called fission. And when they break apart, they become smaller nuclides to possibly get closer to being an ideal isotope of iron 56. So nuclear fission, what is that? That is when a large nucleus, like uranium-235, splits into smaller nuclei. So for example, here we have a slow neutron bombarding the nucleus of uranium-235. That breaks apart and produces barium-141 and krypton, I think it is, 92, as well as some fission fragments, as well as some neutrons. So this is one possible pair of fission fragments. Could be a number of different combinations, and that's what I've said down here. But they're all going to result in the release of energy, and that's what this indicates. So at this point, we're going to stop and look at activity 16A, questions 2 and 3. So you may do those in class tomorrow. Make sure you've written your notes from these slides.